All right, I'm so sorry this is already filled in. I did my third video for the worksheet and then it didn't save it. The file was corrupted, so I have to start over for what is page 3.5. So we had left off with the KRF2 and we talked about this particular AX2E3 is an exception. Normally when you have a lone pair, it's going to make the molecule polar automatically. But this one is an exception because it ends up being linear, so that makes sense that it would be possible to be nonpolar. So because both fluorines are the terminal elements, it's not like one is oxygen and one is fluorine, right? They're both the same element. You've got a pole to the left, you got a pole to the right, so overall nonpolar. So our last main electron group is when you have 6 sites, and that's octahedral. So what I have here is selenium hexafluoride, SEF6. So imagine the center is the selenium. We've got 6 fluorines attached. And so when I look at the main Vesper notation here, we've got our center selenium and then 6 bonding fluorines. So AX6, and that is an octahedral main electron group. All right, so octahedral, one of our main groups here. Whoops, sorry. And in terms of the orbital hybrid, we now need 6 hybrid orbitals. So 1 S, 3 P's, and 2 D's. So 1, 4, 6. There's my total of 6. So the orbital hybrid here would be sp3d2. And what we talked about was, as long as there's no lone pair, which there isn't here on the center selenium, if all bonding elements are the same element, then overall this should be a nonpolar molecule. Now, in the next example, we've got iodine pentafluoride. And what we ended up with here is iodine in the center, 5 bonded fluorines, but a lone pair on the iodine, right? Expanded octet. So this notation here would be AX5, 5 bonding fluorines, and then an E, that lone pair on the iodine. And because of that lone pair, if I imagine, right, one of these bonds now just becomes a lone pair, right, there's still electrons right there repelling the bonding electrons. So the bonding and the lone electrons, they're still repelling against each other. So we still have sort of that main octahedral shape, but now what's happened here is this is a lone pair rather than a bonding pair. And when we look at the shape, it's called square pyramidal. The base of it is a square, right, and then you've got the top. So this would create a pyramid shape if you were to kind of look at connecting all of those base points to the top, right? But now instead of a trigonal pyramidal, like a triangular base, it's a square base. So we've got a square pyramid. So square pyramidal is the shape there. And again, because we have something pulling up, fluorine pulling up, but nothing pulling down, overall this should be a polar molecule, with more of the electron density sitting up here above the selenium rather than below. So we'd have a negative end and a partial positive end. All right, so polar molecule for IF5. Then the last molecule we have is KRF4. And with the krypton, we had 4 bonding fluorines and then 2 lone pairs on the krypton. And so our Vesper notation here would be AX4 for the 4 bonding fluorines and then E2, lone pair, lone pair. And what happens now is we've got the lone pair above and below here. Sorry, there we go, focus. And now what you have is a square for those 4 fluorines, but it's in a plane, right? So this is called square planar. All right, so square planar. And this is the other exception to when there is an E, a lone pair. It is possible for it to be nonpolar. This is the other one, like we saw the linear for the AX2E3. And that's because if we look at this molecule, we've got an electron pull to the left, electron pull to the right, 2 electronegative fluorines offset from each other. We have a pull up and a pull down, 2 electronegative fluorines offset one another. So overall, there's an even pull of the electron density. Nothing's pulling up and nothing's pulling down because these are just lone pairs. So overall, this is a nonpolar structure. The orbital hybrid, we still need a total of 6. The 4 plus 2 is 6, so we still have an sp3d2 hybrid. All right. So basically the rule of thumb is when we look at that Vesper chart, Our orbital hybrid matches the electron group, right? So anything AX2 is an SP. AX3 trigonal planar is SP2. That includes the AX2E. And then when we get to AX4 tetrahedral, this would be SP3. And then the SP3 also applies to AX3E and AX2E2. Now we expect AX2E, AX3E, and AX2E2 to always be polar. All right, the AX2, AX3, and AX4 would be nonpolar as long as all bonding elements are the same. When we get to AX5, we know we've expanded the octet. We've got 5 bonding sites, so we've tapped into the d orbitals. So we have an sp3d hybrid. Same for seesaw, T-shaped linear, they would all be sp3d hybrid. And we expect AX5 to be nonpolar as long as all bonding elements are the same. But AX4E and AX3E2 should be polar no matter what. When we get to AX2E3, as long as both X's, the bonding elements, are the same, I put a little star, that one would be nonpolar because it's linear, that makes sense. AX6 is where we get into 6 attachments, either bonding pairs or lone pairs, right? So that's the octahedral shape, and that is tapping into 6 hybrid orbitals, sp3d2. That same hybridization for square pyramidal and square planar. We expect AX6 to be nonpolar as long as all bonding elements are the same. AX5E would always be polar, and AX4E2 can be nonpolar again if all bonding elements are the same. Because the 4 bonding elements are in that plane shape, right, the planar shape, and they make a square, for every pull in one direction, there's an equal pull in the opposite direction. So overall, that would be a nonpolar molecule. All right, so that completes going over the Chapter 10 and 11 worksheet, looking at geometries, hybridization of orbitals, and whether or not molecules would be polar or nonpolar.